I received some questions recently that asked about some proofs by contradiction. And I really like proof by contradiction. It's a really clever sort of thing, even though it's not taught very much in the syllabus that I have to teach my classes. But I figure, even though it's a really cool method, a lot of people don't know about it. So before I answer the actual questions that I've been given, let me just set out what's the difference between the normal way that we prove things, which is often called just direct proof, and proof by contradiction, which is often called indirect proof, for reasons you'll see in a second. How does direct proof work? Well, suppose for each of them really, you have some statement, let's call it statement A, that says something like, root 2 is irrational. That's a statement, okay? And there's a very famous proof for the irrationality of root 2. Now, statement A, we want to prove that. How would you go about doing it as a direct proof? Well, what you would do is you'd start from things that you know. So is there any known data or definitions, things like what is an irrational number or a rational number? You start from that, okay? And then what you want to do is think about, what kinds of valid mathematical processes or logic can you use to manipulate what you know, like your data or your definitions, and change it so that you arrive at the statement that you wanted, statement A. So it's kind of 3 steps here. You start from what you already can assume to be true, or things that are accepted as true, axioms, definitions, etc. You do some stuff to it, you manipulate it until you get to what you want. Okay, that's a direct proof. That's what we're mostly used to. Now, how does an indirect proof work, or a proof by contradiction? Well, instead of starting from things that everyone agrees on, it starts a bit backwards, because what you do is you take your desired statement, statement A, okay, and you assume that it's false. Okay, so right from the get-go, you're saying, well, let's just imagine, what if it were not true? So assume that not A is true. Now, after you assume that is true, you take this logic. So for instance, in this case, you'd say, well, suppose root 2 were actually rational. So I'm assuming that statement A is false. You do the same thing. You apply some mathematical processes or some logic, right? You manipulate it. And then, now here's why it's called a proof by contradiction. You arrive at something which is, well, as the name suggests, contradictory, something which clearly cannot make sense, or flatly is the opposite of what you actually assumed in the original. Okay, so what you've got is now a contradiction, something which must be false. So if you arrive at a contradiction just by doing totally valid stuff, this mustn't be the problem. The problem must be where you began, right? So what you would do is that you would recognize that a contradiction here implies this assumption to be wrong. So therefore you would conclude that since the assumption is wrong, which is that a desired statement is false, then you conclude that the desired statement must be true. Which is not so hard, but it is a bit of a roundabout way to do things, which is why it's often called a indirect proof. Okay. Now, the question that I actually got asked to prove, one of the questions that I got asked to prove by contradiction, what we're required to prove is that there is no smallest rational or positive rational number. Now, this is interesting. You can see why it might be approached by a proof by contradiction, because it's like, well, where would you even begin if you were to do a direct proof? Like, what known data or definitions would be a good starting point, okay? So what we're going to do is think about what would happen. This is step 1, what would happen if this were false, okay? So here's my proof, okay? And it's going to be a proof by contradiction. I'll start off by saying, well, let's assume that there is a smallest possible, smallest positive rational number. Okay, so if there is a number, I should be able to give it a name. So I'm going to call it Epsilon. Okay, Epsilon's kind of a traditional name for mathematicians when they want to talk about small numbers. Okay, so if Epsilon is the smallest positive rational number, I can say things like, well, Epsilon must be greater than 0, Okay, and I can also say that epsilon must be equal to, and I'm going to introduce some more letters here, P on Q, where P and Q are integers. Okay, now, what am I doing here? I've started with my assumption, which is actually wrong, right? Now what am I doing? I'm applying my valid mathematical processes and logic. Now, what's this line about? P and Q are integers, and what I've introduced is a fraction or a ratio. This is the definition of a rational number, okay? So number one, I've said it's positive. Number two, I've said it's rational, okay? Right, now, let's apply some more logic to this. If this is a rational number, right, I should be able to just divide by 2, right? So if I divide both sides by 2, I'm going to get P on 2Q. But this leads to a problem because since I've already said that Q is an integer, right? If Q is an integer, therefore, if I double Q, that should still be an integer, right? You know, take any integer you like, 3, 4, 5, 6, 200, whatever. If you double it, it stays an integer. It doesn't become, you know, a fraction or anything like that. So therefore, this number here that I've got, epsilon on 2, it's also a rational number because it's a ratio, a fraction, with an integer on the top and an integer on the bottom, okay? So I can say, therefore, epsilon on 2 is rational. Now, can you see the problem? Can you see the contradiction now? Since epsilon on 2 is rational, right? But epsilon is greater than 0, that means epsilon on 2 must be smaller than epsilon, the number I started with, okay? But that's a contradiction because I said that epsilon must be the smallest possible rational number, positive rational number. That's where I started. But now, just by doing some simple maths, I've come up with a new one, right? I've come up with a new smallest positive rational number, okay? So this is a contradiction. Therefore, my assumption at the beginning that there is a smallest positive rational number, it mustn't be true. You know, epsilon cannot exist. You know, it's at the same time, it's the smallest positive rational number and is also one smaller than it, okay? So therefore, I can now come all full circle, right? I can say, well, there mustn't be a smallest positive, and you can write it like this if you like, positive rational number, okay? So that's a proof by contradiction.